In this fifth quantum mechanics lecture, we're going to explore the Schrödinger equation in a little bit more detail. We still may not get to all the maths of applying it just yet, but we will unpack it a bit more. And what does it mean? How can we convert a deceptively simple equation into something we can use? So we will do the Schrödinger equation, we will cover it again. And then what do we mean by potential and kinetic energy, which is what the Schrödinger equation uses. And then we will move on towards how we begin to apply it. So the Schrödinger equation, this deceptively simple 4 letters and an equal sign, it looks like this shouldn't be too much of a trouble to deal with. Maybe you could cancel out these and say that H equals E, for instance, but clearly, that's nonsense. Once you've got to what you've got to understand is the idea of an eigenfunction and an operator and an eigenvalue. And what you can see is that an operator takes in a mathematical function, changes it somehow, and spits out the exact same function again. And specifically in the Schrödinger equation, the function that we're accepting here is a quantum state. It is a mathematical function that describes the state of a quantum object, an electron, a photon, or whatever. The operator is the Hamiltonian operator, and we will break that apart in a moment. And the energy eigenvalue here it's an observable. It is energy. So the Hamiltonian energy is a measure of total energy of a system. It is the sum of kinetic energy and potential energy. So you may have heard of these terms from school level physics or elsewhere. These are what comprise total energy. All we need to know is kinetic energy and potential energy. So what, in fact, are they? Well, kinetic energy, if you look this up, you will see something like a roller coaster. Something's up here. It will begin to move really fast under its own motion. It has kinetic energy. It accelerates, it moves. V, however, represents potential energy. And in this picture, you've got an archer's bow. And what is happening there is it is in a low energy state when it is relaxed. And when you pull it back, suddenly its configuration changes. You are putting energy in there. So potential energy is about a configuration of something or its relationship to other things. If you raise a ball off the ground, its relationship to the ground changes. So its potential energy will change. And you can swap back and forward between potential and kinetic energy. You have to put in a bit of movement to draw a bowstring back, and when you let go, it can produce movement going back. So we will talk about these in terms of their equations a bit more. So kinetic energy is equal to half times the mass times the velocity squared. That's related to momentum as well. And if you're curious about why it's mv squared, do look up, say, Emily de Châtelet, for instance. She did a translation of Newton's Principia Mathematica and added her own notes and commentary, which got us thinking more about terms of energy. So Newtonian mechanics only really worked on momentum, which is P equals mv down there. Emily de Châtelet's work really got us to the mv squared that involves energy. So all that kinetic energy is also related to momentum, and I would recommend on your own seeing if you can find out how these interconvert with each other. It's a very simple bit of mathematical manipulation, but it is good practice to do on your own. Potential energy is a little bit more complicated. It doesn't have a single equation because potential energy is a function of all of that configuration. If you've got two objects with a potential attraction between them, potential energy will be a function of their relative position, their distance, for instance. However, we can say that potential energy produces some kind of force, and that force is proportional to the change in the potential energy over space. And of course, force induces an acceleration, so potential energy can produce acceleration. It can then convert into kinetic energy. So, how do we apply this in quantum mechanics? Those equations then become operators. So instead of just the letters T and V, we put the hat on them to say that they are going to be operators. We saw the kinetic energy example before. Here's Planck's constant squared. Here's the mass. And this upside down delta sign here is known as a nabla or del operator, and it's basically a derivative in 3 dimensions. It's taking a second derivative across the x, y, and z direction. And the potential energy operator is, well, it's simply V of x. It is the potential as a function of space. And as we move on to things that actually have potentials involved, that will become clearer. But for now, we're actually going to stick with simplified models only. We're going to work on things where the potential is actually 0. There's going to be no potential in the particle models we will discuss soon. Potential comes into its own when we're talking about atoms. There's certainly potential energy here, but our particle models, the simplified things we're going to talk about, have none. We're also going to mostly talk about 1 dimension, which means instead of that 3D operator, we've got just a 1-dimensional operator. We're taking a derivative in only 1 dimension. Simplifies down the maths a lot, but illustrates the exact same concept. So, to recap what we talked about there before we get onto the maths, the Schrödinger equation, it's an eigenfunction problem. It takes in the quantum state and spits out the quantum state multiplied by the operator. And that operator H is composed of kinetic and potential energy. Kinetic energy being associated with movement, it's half mv squared, and potential energy, that is a function of configuration or an arrangement. And then what we're going to look at next are some simplified models. We are going to take those operators and apply them to a quantum state.